subject of our substation design division session tonight is circuit breakers. A very important part of any kind of a substation, used in many different places. Basically, a circuit breaker is a device for opening up a current path. When we get into the theory of it, we find that we have a normal current carrying path for the current that the device is intended to carry normally. When we want to operate this for one reason or another, well, then we operate a mechanism that initially tends to separate the contacts. And the first thing this does then is produce an electric arc. Electric arc being a column of hot ionized gases. The temperature of the arc here is in the thousands of degrees centigrade, and this breaks down whatever medium is between the contacts into their component parts. The different molecules break down into electrons and protons, so we have a column of hot ionized gases. Now, in the interruption of this arc, we have basically two different steps. First, we want to increase the resistance of this arc so as to reduce the current through it. And the second step, we want to increase the dielectric strength between the two contacts. Now, there's several different ways to do each of these. First, to increase the arc resistance, we want to lengthen the arc path. I think we can observe this or deduct this from our Ohm's law, and also from our discussion of resistance in a previous session. As we increase the length of any kind of a conductor, the total resistance is going to increase. Now, one of the ways we lengthen this arc is by the actual contact motion itself. If we have a two contacts here, and they tend to make relative motion in that direction. We can see that initially we establish the arc, which is column hot gases between there. Now, one way to lengthen this arc is to move the contacts farther apart. This is one of the things we do. The other thing that happens is that another way to lengthen this arc is by a magnetic field. As we know from some of our other previous basics, if we have a conductor in motion in a magnetic field, why, we can get a force in a given direction. And with proper location of the magnetic field, which we'll get into later, we can make the arc move in one direction or another. Any kind of a heated conductor, a heated column of air or gases would tend to rise. So we'd like to make the arc move in that direction. And in moving in this direction, the third way that we will lengthen the arc is to introduce obstacles in the arc path. If we get these conductors farther apart and say introduced into this arc path, which is going in a direction like that, if we get some insulating materials in this path, this would mean the arc is going to tend to follow the surface of that path there. And this again would be another thing that's going to lengthen the path. It's going to increase the arc resistance. Second thing we want to do is to cool it. In cooling the arc, we would tend to deionize the gases. That means allow or force or tend to bring the conditions about that will combine the electrons and the protons and get back into the original materials that we had to begin with. And we can do this, one thing, by having the arc in a cool medium, which might be a tank of oil. This would tend to cool off any hot conductor that's immersed in the oil. Any contact with the insulating surfaces here that we mentioned would tend to cool the arc, because any heat in the arc path is going to tend to be absorbed by the insulating path there. In extinguishing an AC current arc, of course, we have one distinct advantage, in that the current in a 60-cycle system goes through zero twice every cycle. So at this point, the arc actually goes out, and then when it starts the opposite polarity, it starts up again. It has to be reignited. So as you can see, what our objective here is to, during the period when it goes through the current zero, is to try to increase the arc length, increase the dielectric strength in these periods of current zeros, so that at the next current zero, there isn't enough voltage across the two contacts to reestablish the arc, and then the arc would go out. In increasing the dielectric strength here, one way of doing that, of course, is introducing new material, fresh, cool material into this arc space here. And we can do this by several ways. In several types of breaker, we do it by a blast or forcing air or oil or some other gas into this space here. This would tend to cool the contacts, cool the arc, establish the original dielectric strength between those two contacts. Now, we might see just exactly what we're doing here. In a typical circuit, we just have a source of electricity, and on a single-phase basis, we have some resistance and some inductance in the circuit, and we call that a circuit breaker. We have a circuit out here, and of course, we have a complete path, and we have some capacitance in the circuit right there. Now, if we were to have a fold out here, this is going to be the voltage here across this capacitor. It used to be. Voltage across that capacitor, as long as the circuit breaker is closed, with this closed down here, it's going to follow the normal sine wave. Well, suppose just at this particular instant we have a fold. In that case, fold with these 2 points shorted together is going to drop the voltage across this capacitor to zero. And in the meantime, the current is going to increase to quite a value. Now, voltage across the capacitor remains zero till a point, say a second time later, the circuit breaker contacts have parted far enough so that the fault is cleared. And at that time, at the next current zero then, at this point the fault would be cleared because the current would be going through a zero crossing right there. However, I think we can see that in a circuit that's primarily inductive, which is the case we have in most transmission lines, the voltage across the contacts might be the maximum, because in an inductive circuit, in a completely inductive circuit, why the it's going to lag by 90 degrees. And let's see, so this would mean that at this point, by the fault is cleared, the voltage across this capacitor, since the current flowing here would tend to continue through the inductance, the voltage across the capacitor would tend to jump up to the maximum initial value there. However, because of the charging of the capacitor, we have kind of an oscillatory motion so that the voltage jumps up to that point at a higher value, then tends to oscillate around the sine wave until it gets back to the normal sine wave. Now let's look and see what some of the basic parts of a circuit breaker are going to look like. And we might just do this on kind of a functional basis first without talking about any specific kind of a breaker. First of all, we have a continuous current path. We have to have a conductor that's going to carry the continuous rating of that particular circuit breaker. This is the load current, the normal current through that line. We have to have some kind of a insulating structure to maintain the line to ground insulation at all time, and when the circuit breaker is in the open position, we have to have insulated for the full line voltage at all times. And we have to have basically a arc interruption mechanism. This is the device that's going to interrupt the arc. It's going to increase the dielectric strength between the contacts so that this piece of equipment can function as a circuit breaker. And then finally, we have to have some kind of a operating mechanism that we can control. We can operate it remotely. Now let's get into some of the specific means we use in equipment to accomplish some of these goals. Now, one of the first types of breaker we're going to look at is an air breaker, in which we use several of the means that we described in order to extinguish the arc. First of all, let's just kind of briefly go over what it is. And this is a sketch. We may see more of it later. We have the normal contacts, these 2 points right here. And when the breaker's closed, these are in close proximity. As the breaker starts to open, we get an arc formed between these 2 contacts here. That's just indicated by the 1 right there. Now, the contacts then continue to open, shown by these different positions here. And this tends to extinguish the arc by increasing the contact separation. As the contacts are separated, the heated arc column tends to rise through the different positions shown as 2, 3, 4, and 5. As it rises, it eventually intersects these plates called insulation plates. They're made out of a ceramic type insulating material, so that the arc is forced into a series of jagged edges there. This tends to increase the arc length, and contact with these plates cools the arc surfaces. As the arc started its upward path, it contacted what's called the front arcing horn and the rear arcing horn over here. And connected to this rear arcing horn is the blowout magnetic core here. And as the arc reaches this point, it has a current path around this magnetic core here, and producing a magnetic field that tends to move the arc in this direction too. So we have about 3 or 4 different ways there that we cool and extinguish the arc. We have a normal set of current-carrying contacts here, and then we have the arcing contacts, really to say the burning of the contacts during this any kind of interrupting process. Now, second means of arc interruption that we discussed is by arc pressure. This is too good a drawing here, but as we can see, we have a chamber here inside the circuit breaker. It's composed of a series of contacts, either contacts here and here, that move apart, and in doing so they generate an arc at points, this point right here and this point right here. And around this contact is a series of plates that have different holes opening up to the remainder of the oil in the tank. So when we have an arc generated at this point, and in this little detail here, we have an arc generated at this point right here, we have a tremendous increase of pressure here. The gas, the high temperature arc, breaks down the insulating oil into hydrogen and carbon, and that gas then increases the pressure and forces oil out of this particular point here, but around into a directed path into some of the other holes in this chamber. And doing so, it flushes out the arc products coming back up through the arc as the arc is lengthened here. And you see in the second picture we tend to move apart, and this force here, it's a self-generated arc. It tends to cool, and it increases the pressure at the specific point, and the oil, being somewhat practically incompressible, will not compress, so it is forced around in another path past the contacts to increase the dielectric strength there. Question that might easily come up is we're using this arcing contact under oil. Why doesn't the thing explode? Why don't we have burning here? And one of the answers being that we have the contacts deeply immersed in oil. So first of all, there's no oxygen present. So although we may have arcing, we cannot have a tremendous explosion that we have if oxygen were present. The hydrogen itself, the bubbles of hydrogen that are formed, are cooled as they bubble up to the top of this oil surface, and by the time they get to the top there, they're of a cool enough temperature so that they will not explode or burn at that particular point. Now, another way we use to interrupt an arc that we'd mentioned is by an oil or air blast. And this particular circuit breaker, we can see the contact structure here similar to what we had before, but at this particular breaker we have an oil pump at this point right here, so that when we have an arc there, a low current arc, it's formed in here, but the pressure isn't really sufficient to produce a high enough, or the temperature of the arc and the arc energy isn't really sufficient enough to produce a high enough pressure to do a good job of putting out the arc. So in this particular manufacturer circuit breaker, we had a pump that directs a stream of oil through the contacts and past the contacts to make sure that we get interruption at the lower current values. As we go to the higher current values, there's enough arc energy in the arc itself so that it develops a high enough pressure and it cleans out the space here and establishes the dielectric strength. The oil pump is still working at that time. After the arc has been extinguished by the self-developed pressure, the oil blast helps the cleaning away of the arc products there. One of the big problems on circuit breaker of this design is not so much the high capacity faults, the faults at the extreme end of the range, but actually the other way around, the faults at the lower end of the range, because this means that all the designs have been based on producing a certain amount of pressure under an extreme condition. Here you have a very a very small amount of current, and this means that quite often you do not develop enough pressure to produce the desired effects. I want to mention one other thing. On both of these last two types of breakers, I guess we can see it a little better in this one. Another way we use to extinguish arcs is to put a number of breaks or interruptions in series. That means the voltage to be interrupted across each one of them is a lesser part, and therefore it's easier to establish the dielectric strength. This particular one, where we have an intermediate contact here, and then an arc space or a break here and here. And we'll see later in some of the other breakers we have this same situation. Now let's look at the second point we want to mention. That's the insulation structure. And to do that, I'm going to put on a type of an oil circuit breaker that'll illustrate several of the things that we've talked about. This is a 69 kV oil circuit breaker. These 2 points here are the terminals that we connect our power connectors. This structure from here down to here is the porcelain bushing. The bushing itself, to those of you that may not be familiar, is has a center conductor around which is rolled a series of paper cylinders separated by oil. That is, the entire interior there is oil impregnated. And these paper cylinders are sized so that you maintain the same voltage across each cylinder. This is what's called a capacitor or condenser type of bushing. And on the outside of this, we have the porcelain protection from weather and also from voltage flashover from the power or the line terminals to the grounded case. But to continue, the current path would be through the bushing, through these devices here that are called current transformers, and we'll talk about them later, to the bottom of the bushing. At this point, we have the circuit interrupter molded to the bottom of the bushing. This is the device that we'd mentioned in the two earlier transparencies that interrupts the arc. And then coming out of the bottom of that is the moving contact. This happens to be one of the contacts there. As you can see, we have a current path over here and another contact here. So on this particular type of circuit breaker, we have 2 breaks in series. And then on the other side of the circuit breaker, we have the same type of an arrangement with the interrupter mechanism and the bushing. All of this is encased in oil inside the metal tank shown there. Oil is used as the major insulation inside the tank. It allows much closer spacing of all the components. As you can readily imagine, this tank is probably some 3 feet in diameter, but yet we have energized surfaces, or as I recall, basically 8 to 12 inches from a grounded surface there. There again, due to the high dielectric strength of oil. Other types of circuit breakers would use different media here. We have circuit breakers in which some of the insulation in here is compressed air. Compressed air has a much higher insulating value than normal air. Another type of media there is sulfur hexafluoride, which has a much higher dielectric strength than plain air. Some of the other components that are used here, this operating rod here that moves the contact open is made out of plastic or wood in some cases. As we mentioned, another component of the circuit breaker is the metal tank. It houses the oil It provides a mounting structure for the opening mechanism, which we'll talk about a little bit later. It has auxiliary equipment, valves to draw out the oil. It has a frame to support it. Now, as we'll see in some of the later slides, this particular unit is supported by a framework that is attached on these channels right here. The bushings themselves are bolted to the tank at this point right here. To say this is a oil circuit breaker, we might briefly mention and show the air circuit breaker. This is a draw-out circuit breaker in which the frame is mounted on wheels so that it can be wheeled in and out of a compartment. These are the bushings shown here. The studs here, or the contact fingers here, match a stud in the switchgear cubicle that we'll discuss during our next session. These plates here are the arc chutes that would cool the hot gases as they rise. But in this case, this is a framework for moving the breaker in and out. Now, the operating mechanism actually performs several functions. Basically, or simply, it opens and closes the breaker contacts. It's useful, and all the breakers have means for closing these contacts either by a gear or by a crank or by a lever at a very slow rate by hand, so that the contacts can be adjusted initially if they all meet at the same time and the timing can be checked. They also have means for operating them remotely by electrical devices, control switches and coils, either by a control switch, a handle that a person turns in the substation or at the circuit breaker, or automatically by protective relays in the substation control cubicle. This happens to be a 69 kV breaker, but it illustrates some of the points on the operating mechanism. All the circuit breakers we have, with one minor exception, operate on the principle of being tripped, that is, opened by a compressed spring. So during the closing motion, closing the breaker contacts, you compress a spring. So you don't have to have power, other than a small amount of DC power to trip the breaker. You can always trip the breaker. You may not be able to close it, but you can always trip it. And in this particular 69 kV breaker here, as you can see, right at the end of the breaker mechanism, we'll point this out, you have a compressed spring here that basically moves this amount D. As I recall, some 6 to 7 inches, depending on the type of breaker. This is a mechanical linkage here that moves these contacts from the closed position shown here to the open position here. And in a 69 kV breaker, this is in the order of 12 inches. The linkage to an operating compartment that houses really the power source is usually mounted at one end of the circuit breaker. As you can see, mounted in this position here, so that any power source here is transferred or translated through the gearing here to move the contacts in an up and down motion. On the circuit breaker, we also have the current transformers that we mentioned in an earlier slide, these are mounted on the 69 or on the bushing itself inside the tank, and they're used for metering, relaying in connection with the particular circuit. In all of our circuit breakers, these current transformers there are a Mulder ratio, as you have the opportunity of many different connections. Each bushing has the opportunity for mounting 2 sets of current transformers there. In this case, the primary winding of this current transformer is the single copper conductor through the center of the core, and then the current transformer itself is in a circular shape that fits right around the bushing. Now we might get in some of the details of circuit breaker classifications. These are just some of the terminology that you hear. The tank or housing that we pointed out can either be a dead tank or a live tank. Actually, you get the opposite effect when you touch the tank. If you touch a dead tank, you're alive. If you touch a live tank, you're dead. So I don't know where they got that particular terminology. The dead tank indicates that the tank or framework or whatever you're holding is grounded. It's de-energized. You can't touch it during normal operation of the circuit breaker without any hazard. In our 69, well, let me back off there. One type of dead tank circuit breaker is called a 3-tank, in which you have 3 separate tanks mounted on a single framework with each of the 3 phases in its own tank. This type of circuit breaker is used in our system at various points from 15 kV up to 345 kV. We have started, or we've had several single tank breakers at 15 kV for quite a while, and we're just now starting to install some 69 kV single tank breaker. These are breakers that have all 3 phases, all 6 interrupter mechanisms and bushings in a single tank. And this gets kind of crowded, but it performs the same function. As you can see, we have single tank diameter, I don't have the figure handy, but it's in the order of 3.5 to 5 feet, depending upon the manufacturer, in which we have all 6 bushings around the perimeter of the top of the tank. Then we have a contact mechanism for each phase in the same tank. The other type of breaker, the live tank breaker, on our system is only used at installation from 161 kV up. And we'll briefly show this slide here, which is a sectional view of our 345 kV breakers out at Hills, in which the breaker operating tank itself are these 3 tanks at the top of the porcelain insulating columns there. So in this case, this is the live part of the breaker. The normal current carrying path is coming in this contact through a bushing there, through this mechanism here, straight through the 3 interrupters in series. And this illustrates several things. At 345 and higher, one means you use to interrupt the arc is just the number of breaks in series. At 345 you have 3. At higher voltages you have 4, 5, 6. And inherently at the extremely high voltages you have to go to a live tank circuit breaker. You can't get a big enough dead tank circuit breaker to contain the 300, well, you can at 345, but you can't at 500 or 750 kV. We do have a 345 kV oil circuit breaker out of sub 56 now. But once you get higher than 345 kV, just the mechanical, the physical problems just get too big. So you have to go to a live tank type construction, which is quite complicated, but it's the only thing that'll do the job. As we mentioned earlier, another type of breaker mechanism is the draw-out type of construction. Now, the different types of interrupting mediums, ways of interrupting the arc, we have an air or an air blast type of principle. On our system, we have some 15 kV air blast circuit breakers out at Riverside in the station, where we have a draw-out type breaker, similar to what was shown in some of the previous transparencies. But as the contacts start to part, we open up a valve and direct a stream of compressed air past these contacts. And we use the same principle on some of the 161 kV breakers at Fort Dodge and on the 345 kV breakers. I wanted to show you a brief view of the interrupter head on one of the 345 kV circuit breakers. This isn't a very good drawing to show the actual current path of operating mechanism, but I put it up here to show that it's a much more complicated type of mechanism. Basically, we have our current path is in here, around the shell, and out the other side. And then when we want to interrupt the arc, we open up valving farther down here, and we have a stream of compressed air at, I believe it's 500 pounds. Somebody could correct me on that one. Past these contacts right there, which blast the arc out by lengthening it and putting in the compressed air in this space fast enough so that we can interrupt the arc. Another type of medium is the oil, which we've discussed several times, so I won't go into that. Thought I'd show you briefly a vacuum circuit breaker. It would seem vacuum has the ideal characteristics of circuit breaker. Once you get the contacts apart with no type of medium in there to transmit any kind of an arc, it would seem to be the ideal circuit breaker. And in fact, it is, and probably will be used more and more in the future. The problems in the past have always been the manufacturing problem. How do you get a good vacuum seal that'll last for years and years? And the manufacturers within the last 5 and 6 years have been starting to solve these problems. We have some vacuum enclosures at sub 73 in Comanche that have been there for 6 or 8 years probably, that I know the substation personnel are very well satisfied with, and we're thinking of getting quite a few more. But basically, a vacuum circuit breaker, you have the entrance bushings here attaching to either end of a vacuum bottle, and one end to a bellows arrangement. We have an operating rod that can move the contacts closed and then open them again. Because of the vacuum, they don't have to move very far. In fact, it's about 3/8 of an inch at 15 kV. And this is kind of a view of that bottle that we were showing on the other one, where we have a moving contact rod and a bellows arrangement here to allow movement, and then a ceramic envelope around the contacts, and then different arc shields here. These are the contacts themselves, and the stationary contact here. So on operating this type of circuit breaker, we just move these contacts here a very short distance, in the order of 3/8 of an inch. We interrupt an arc at 15 kV. I think we get through one more basic area first, and we'll have our break. Of course, the thing that makes all these circuit breakers work is an operating mechanism. One of our other slides gave a kind of an idea of how this worked. This maybe helps a little bit better. We have some kind of a power source in a compartment at the breaker, and it operates an operating rod here. It goes in up and down motion, so it translates the motion of the operating equipment to this rod here. This rod here translates that motion at 90 degrees, so we move back and forth in this direction here. At each breaker pole, or for each phase, we have another gearing arrangement that translates the motion in this direction to one up and down. And that is the motion that closes or opens the breaker contacts. And during the closing operation, we compress this spring here. And then when we want to trip it, we release that spring. So as you can see, this part of the circuit breaker is a mechanical engineer's dream or nightmare, depending on how you want to look at it. But it's a continual system of levers, linkages, things going in every direction. Now, the power source can be one of quite a few different schemes. One that our company had used for quite a while and still uses from right now it's used on 4 kV and 15 kV breakers and some of the older 69 kV breakers is a simple DC solenoid. This requires a 125 or 250 volt DC battery because you have to have quite a bit of current to provide enough force to move this rod up and down. But it's still a simple mechanism, doesn't require much maintenance, and I think our company would still be buying these at some voltage levels, except the manufacturers don't want to make them anymore. This slide here doesn't show much, except this is the type of mechanism we have there, and we'll have a slide that'll show that in much greater detail later. This also gives you another idea of the mechanical linkage, where this is the operating rod here, and this is the linkage that moves the contacts up and down. This solenoid is, just as I said, it's just a big coil. And it's shown right here. This moving, closing solenoid. See if I can get myself straight here. Yeah, this is the coil right there, in which you pull this rod up and down, and that in turn moves the breaker. So it's very simple. There's really not much to it compared to some of the other types of operating mechanisms. On our oil circuit breakers from 69 kV up to 345, probably the most common type of mechanism is a pneumatic mechanism. This is a kind of a view of the control compartment. We've got a lot of equipment in here. Takes quite a bit of maintenance, and there are different things to go wrong, but it still provides a means of storing operations at the breaker and allowing a breaker closing just by energizing a coil or an electrical circuit at some remote place. This is kind of a schematic of what a pneumatic operating mechanism look like. We have an air compressor in each control compartment that's powered by an AC motor, and in turn it compresses the air up to pressure. And most of our circuit breakers, it's in the order of 250 psi. On our 345 kV breakers, we have several systems, but we compress at about 2,500 psi, and then we reduce it. So we compress the air, we store it in a tank. This means that we have some stored energy there, sufficient for about 5 operations with no more source of power there. If we lost our AC supply to the air compressor, we still have the possibility for 5 closing operations. Remember, we can always trip the circuit breaker. And in connection with the air compressor system, we have the governor switches, low pressure alarms and different supply valves to operate the air system. Another type of system is a hydraulic system. In this kind of a schematic, we don't have time to go into some of the details, but basically we have an accumulator here where we hold a fluid that is compressed under a high pressure in the order of 3,000 pounds here, and we use this stored pressure to operate this cylinder here to move the operating rod up and down. One type of mechanism that we're just getting into now is a motor-operated spring, which has been used at 15 kV, several locations, and we have just purchased our first 69 kV circuit breakers with this type of a mechanism here. What we do, we have a motor which winds up a closing spring through a pawl. This is another one of these mechanical engineers' pride and joy, which we have a motor here that turns a gear that turns this driving pawl in little spurts here. So we compress a closing spring until we have reached a certain value that we pass the cam, and then we transmit this energy through the pull rod and close the breaker contacts. Well, I think we've covered some of the basic ideas of circuit breakers as far as the major components, the type of tank for housing, the type of interrupting medium, the medium for interrupting the circuit, and then finally the operating mechanisms that are available to open or close the circuit breaker. So let's take a break now. Let's try to be back by 6:30.